This is the 10th video on electromagnetism for A-level physics. The aim of this video is to understand Lenz's law and how to use it. Up until this point we have talked about how EMF is induced and the factors affecting its size, but not the direction of EMF. Prior to this we've considered loops like this. Let's take a circular loop like that. Let's say that we have a magnetic field, a uniform magnetic field passing through it like this, straight into the page. And then we change the flux, we change the amount of field that passes through, and as a result we induce an EMF, and if this is part of a complete circuit we'll get a current. Well, what we haven't established in the other videos is whether the current would go around the loop that way or whether the current would go around the loop the other way, like that. So whether it would go anti-clockwise or whether it would go clockwise. This is actually what we're going to use Lenz's law to establish. Okay, so we'll state Lenz's law. Lenz's law, the direction of the induced current is always such that it opposes the change that produced it. At first glance that's not particularly clear, it doesn't seem very useful. We're going to get into the details of it with some examples. Just before that we need to recall something from GCSE. We need to recall the idea that when current flows through a wire or round a loop, a magnetic field is created. Okay. Something else that we need to look into is the right-hand grip rule. The right-hand grip rule relates the directions of the current in a wire or a loop and the direction of the resulting magnetic field. Here we're going to stick with loops. So for a loop, the fingers follow the current around the loop and the thumb sticking straight out follows the magnetic field. So let's look at an example of this. Let's say that we've got a loop like this and we send a current around like that. So the current's going clockwise. So the fingers of the right hand need to all point around like this. Well, the only way to do that is to take your thumb, point it straight into the page, straight into the screen, and you'll see that your fingers follow around in a clockwise fashion. They go over the top and under the bottom of the loop. Well, because the thumb is pointing into the page, that tells us that the magnetic field produced by this must be directed straight into the page, like that. Let's look at more of a 3D picture. So let's say we've got a loop that looks like this. And the current goes up the front and down the back. In this case, the fingers of the right hand are going to go around like that, so it's up the front and then down at the back. If you go through and do that, you'll end up finding that your thumb has to point to the left, and that gives us the direction of the magnetic field. So the magnetic field will have to be pointed through like that to the left. Just complete those lines. Okay, so that's the right hand grip rule, and we're going to end up applying this when we consider Lenz's law below. Okay. Let's consider a bar magnet approaching a coil. We'll use a coil that's got a single turn to keep things simple here. Here we have our bar magnet on the left with the field coming out of its north pole. We've left the south pole out, it's not going to affect the problem. On the right we've got a circular loop. It's placed on 3D axes to give a little bit of perspective. We need to pick the magnet up and move it, because in accordance with Faraday's law, the only way we're going to induce an EMF in that coil on the right there is if we change the flux through it. So you can see now the red, blue, green and even yellow field lines are passing through that loop. We've changed the flux through the loop, so we've met the criteria to induce an EMF, but now we need to determine the direction of the EMF and really the direction of the current that flows inside that. So we'll just put the magnet back to its original place to make the diagram a bit easier to look at. Okay. Lenz's law contains the phrase, the change that produced the current. We'll work on just breaking that down now. So what exactly was it that happened here that produced the current, that induced the EMF? Well, it was the increase of rightward flux. So all of this flux, in fact the yellow line was included as well. So it's the change is the increase in rightward, as in just flux that's directed to the right, with arrows that are vaguely pointing to the right. Increase in rightward flux through the loop. That there's a directionality to this, to increase in rightward flux through the loop. Lenz's law also refers to opposing this change. So some current flows inside this, either that way or that way, and it needs to be the direction that will allow the loop to oppose that increase in rightward flux. Well, if we've got an increase in rightward flux through that loop, then we need to have the loop produce its own leftward flux to counteract. So we'll see that best with this side-on view of the loop. So it's going to produce its own field and it's going to be directed to the left, like that. Right, this would be the leftward flux of the loop that opposes, right, that key word opposes from Lenz's law, the change. So then let's apply the right hand grip rule and see what direction of current we must have in order to get that leftward flux. So again we'll go for a vaguely three-dimensional picture. I'll say that's the front of the loop and that's the back of the loop. We've decided that there's a leftward field, so with the right hand grip rule, the thumb follows the field with a loop. So if the thumb points to the right, if we're doing that and you point your fingers straight up from your thumb, so your thumb and your first finger make a sort of L, you'll see all of the fingers are pointing straight up, and that means that the current is going up the front of the loop. And then if you were to curl the fingers around as if you're trying to just grab something with your 4 fingers but keep your thumb in the same position, the fingers then point down. So the current is going up the front of the loop like that, and coming down the back of the loop like that. And that's how it manages to oppose the change that it was initially subjected to. As we've seen when we just apply Faraday's law, pulling the magnet away will also induce an EMF, and that should have a direction to it as well, or it should produce a current that's got some direction. I think common sense would tell us that everything's just going to be reversed. If we're pulling the magnet away, then it should lead to the reverse effect of pushing the magnet towards the loop. But let's work our way through this again. So the magnet is pulled away. Let's look at that up here with our magnet. Just get rid of those circled field lines. So we'll take our magnet and we'll put it in this position where it's close to the loop, right? Lots of flux going through the loop. If we hold it still, there'll be no induction because we're not changing the flux. It's just a steady high flux. But watch carefully, as we pull this back, the yellow field lines no longer go through the loop. And then after that, the green field lines will no longer go through the blue. And we've now decreased the flux significantly. We've changed the flux. But what we've done very particularly here is we have decreased the amount of rightward flux through the loop. We've decreased the amount of rightward flux through the loop. In accordance with Lenz's law, the loop is going to respond in opposition to this. So to oppose this, the loop will produce a rightward field. A field with field lines directed to the right. So if we draw out that loop, and we put on the field line, so say it's going to the right like this. There you go. The dashed lines are just to improve the perspective, to show that the field is on the other side of the loop at that point. So again, this side here, I'm making a bit thicker, that's the front of the loop. We need to use the right hand grip rule here. We take the thumb and we direct that to the right, just point it straight out to the right, and that gives that's just following the direction of the field. And then the current must be directed up the back of the loop and down the front, because when you curl the fingers, when the thumb's pointing to the right, the fingers will point down at the front, and at the back they're pointing up. So you get this: at the back of the loop the current's coming up, at the front of the loop the current's coming down. Well, that's the complete opposite of what we've got right here, and we'd expected that. We'd expected go through the opposite process and get the opposite result. Okay, let's look at some other questions. We will consider a magnet, well, a set of magnets dropped through 3 different rings. we'll consider a copper ring. So the ring is placed horizontally like that, and the magnet up above is going to be dropped through it. So it's going to accelerate down through like that. So that's our copper ring. I'll draw out the others. We'll consider a ring with a split in it. So just to emphasize that, at the ends there, that they're not connected to each other. There's a gap. We'll drop a magnet through that. And then finally, we'll drop a magnet through a nichrome wire. This is just a higher resistance wire, and that wire has been turned into a ring as well. So again, this is copper split ring, and this is a nichrome ring. In each of these cases, the magnet will actually behave differently. In the case on the left, where we've got the copper ring, the magnet will fall through, and as it falls through, its flux, right, we can see some of its field lines there, will start to pass through the loop, and as a result will induce an EMF in the loop, but the direction of that EMF, or the current that results, it's in such a direction so as to oppose the change that produced it. Well, the change producing it is that magnet falling through the loop. So essentially, when the magnet, is quite close to the loop, like that, and it's trying to fall through the face of the loop, right? It's not gone through just yet. It's going to be being pushed back against like that. There's going to be some force against it. Of course, the larger force here will be the weight of the magnet. But if there's this blue force, the magnetic force, opposing the weight, then the acceleration of the magnet will decrease. The magnet will not go through the loop so fast, it won't pick up so much speed. I want to note that. The magnetic force, and that's the one we've marked in blue as F, opposes the magnet, or the magnet's motion and weight. Hence, the acceleration of the magnet when it's sort of approaching this ring or close to it is going to be less than g. It's not going to accelerate with free fall. In the second case here, the one with the split ring, the one in the middle, an EMF is induced. It's got to be induced because the flux through the ring is going to change significantly. Almost none of the flux is passing through the ring to start with, but once the magnet is really close to the ring, practically sitting on top of it, right there on top of its plane, like that, all of its flux is going through. Just draw in dashed lines to show that. So there's definitely a change in flux, so an EMF must be induced. An EMF is induced because flux linkage n phi through the loop changes. But the really important bit here that leads to an important difference is that break there circled in green. The circuit is not complete, right? The loop is an incomplete circuit, and as a result, no current flows, and the ring does not produce an opposing magnetic field. So in this case, provided we're ignoring air resistance here, the acceleration is equal to g. The only force that this magnet experiences on its way down is its weight. Just put that in there, weight. There's nothing else slowing it down. Then we'll look at this third case over here. So we've got a nichrome ring. Now, the only real difference here is that nichrome has a much higher resistivity than copper. Note that. Nichrome has a much higher resistivity than copper. As a result, even though the same EMF is induced in all of these loops, the magnet falls in roughly the same way, at least as it approaches the ring. The resulting current is smaller. Right? We're looking at same EMF, voltage, but higher resistance. And as a result, a lower current. The size of the current controls the size or the strength of the magnetic field. And I'm now talking about the magnetic field of the loop. So it controls just how much the loop is able to push back against the magnet. So when this is pretty much sitting on the plane about to go through the loop, there is still a magnetic force. It's important to show that it's small. And the weight is the same. Gravity hasn't changed for any reason. There's the weight. So as the magnetic force opposes the weight, it decreases acceleration, so it takes it down from g. So again, g is greater than a, but if we call the acceleration here a3, and the acceleration in the middle a2, and the acceleration on the left a1, we can rank them. a2 is the greatest because this split ring produces no magnetic field. It doesn't fight back against the approaching magnet. Then a3 is the next biggest because there is some current flowing inside this, but it's not really that big. And then a1 is the smallest because we get the largest current in this ring here, in the first case. So we then get the largest field from the loop, which gives us the largest force pushing the magnet away, stopping it from getting through the loop. That's the idea. Okay.